Alright, so where we now in the course is essentially we've gone from the displacement fields, we've differentiated that, be able to relate that via two material parameters using the generalized Newton law, take the strains to stresses, and now we're sitting with a stress field, which is a function of x, y, and z. Okay, so we've got that stress tensor, or that stress vector, that 6x1 vector that we've constructed now. That is now a 6x1. That is a function of x, y, and z. So it's some field. Okay, so that is what we have. But what I want to do now is just first ask ourselves, what are the conditions to make sure that that stress field is even in equilibrium? And to be able to answer that question, we're going to first look really at sort of any arbitrary kind of body. So this is often called the potato. So just an arbitrary body. It can be a car, an aircraft, it can be anything. So on this arbitrary body that we have, or the structure that we're looking at, we might have some places where we have, like here at the bottom, prescribed displacements. So this is now indicated in the textbook by SU as prescribed displacements. That's when the displacement is equal to 0. Obviously, we can have maybe even parts that also have prescribed displacements, but the displacement is not 0, but we are pulling on the structure with a certain amount. That is also possible, where we say, take this point and move it that far. And then if it's fixed here, the thing will have to sort of bend and get pulled towards that direction. So that is all what this sort of signifies. Okay, we essentially sit with possible point loads we could apply to the surface of the structure. We sit with traction surface structures we could apply to the structure. So these are just normal loads like newtons that these P's represent, and these surface tractions we'll see a bit later exactly what they are and what they relate to. But these surface tractions are really important. A way for us to be able to see this distributed loading that we have. So surface tractions really are newtons per area. So similarly, it's Pascal units. So it's similar units to stress, but it is saying we're applying a load over a certain area. So this is Newton per area, the units of this. And if I integrate over the area, I would get something that's just the resultant force that acts there. Okay. Additional loads that we could have is essentially body forces that could act on the structure. Okay, so we could also have body forces acting on the structure. And these body forces are essentially given by these fx's, fy, z. So this is maybe gravity in the x direction, it could be gravity in the y and the z direction, if you're on an awkward planet. But on planet Earth, we're sitting with gravity in one direction. But body forces is not only due to gravity. Body forces could be a function, could be a result of electromagnetic forces acting through the body. It could be a result of accelerations. So there's multiple ways we can actually invoke body forces. And what's the difference between a body force and sort of a point load and traction is that a body force acts at every point in this volume that body force acts in. So at every point in this body really experiences a body force, where the load is really applied here at the surface. That's where the load is applied. And here essentially at the top, the surface traction is applied sort of here at the top of the surface. Okay, so the question is, what is the units of these body forces? Also, the units of the body forces are typically Newton per volume. Okay, so that's units typically that you have. So if I take a Newton per volume and I multiply it by this volume of the differential volume, this fx dv then becomes just Newton. So this is then this fx times this dv is got unit Newton that acts there, and there's newtons that acts there, and newtons that acts there, if I were to multiply by the incremental kind of volume there. And so what this little cube signifies here is any point in the structure. So if I take my hand where my hand is and I zoom in there, I get to this little representation. So this is sort of an infinitesimal small little representation of a cube. And then we want to ask ourselves, what is going on in the inside here of the cube? Okay, so what I'm going to do is I'm going to first just sort of go through pulling that cube out by going to the next figure, and then we're going to start looking at what are the sort of relations of equilibrium that's required there. So we are going to be living now in the stress world, and then I'll follow up with a video just to explain why is this all of a sudden an important thing. Why can't we just do sum of forces anymore? Because we already have forces here acting here. Why can't I just do sum of forces? And why do I have to go towards stress components? Why is that critical? But before I get there, I'll just want to give you sort of a good understanding of the equilibrium conditions behind this. Okay, so I'm pulling out this cube now, and I'm putting it in space, and then I'm saying, okay, let's get the most general case we can of putting all of these surfaces, what kind of loadings they might have been. Okay, so if you look at what's going on, there's the body forces that I have, but they get multiplied. So Newton per volume gets multiplied by the volume. That's just Newton units. So that's sort of from that middle of that little infinitesimal cube. This dV tells me what is the volume of this little cube. So it's essentially, it's a, let me see where's the x direction. So it's dx, dz, and essentially dy. So that is how the coordinate systems were chosen. So that is essentially what that is. So that's dx times dy times dz is essentially dv. That is that volume. And if I look at the back face of the structure, I'd say that there's on the normal component, there could be a stress component acting normal to that surface. There could be stress components acting in the plane there. So this is a sort of much general version of stress that could act on that plane. So we have three components that could represent some kind of thing or traction or something on that surface. Okay, so that's that stress component. There's the two shear components. And then as I move through this body from the back to the front, these stress components through this little incremental body could change. Because it's although it's a very small body, you've seen that those sort of fields, the expression that we have is a polynomial, so it's some kind of field expression. They do vary over time, so, over space. So if I move from one point in space to another point in space, that stress field might vary. What we understand is what kind of variations are allowed, or if there are variations allowed, let me put it like that, what makes sure that they are in equilibrium? That we don't just end up with saying, okay, let's just have variations of stress, but then things are spinning and accelerating out into space. We want to make sure that this thing is still in static equilibrium. So this sigma xx component, as I move through the body here, as I move a distance dx, it could have changed because of variations of how that sigma x could change as a function of x, and I've moved the distance dx from back to front, and that is that contribution. So the stress in the front is now potentially sigma x plus a variation of that stress times dx. So that is what we have there. And the same holds then for the shear components going from the back face to the front face. There's variations that get added. And if I go towards the left-hand edge here of the sigma y, with the shear components acting on this face, as I move across the body here, there's again variations because I've moved now in the dy direction. All of the variations in terms of dy could have caused the stress that was sort of a certain magnitude here to be slightly larger or smaller, depending on what kind of stress field we have, loading that we're applying. And so essentially, if I go to the bottom, the same story holds. Okay, so that is really what this boils down to. It's just inconvenient to look at it. There's lots of symbols here and stuff. So I like to just, let's pull out a 2D version of this, and let's ask the questions on the 2D plane version. It's not, we don't lose anything from a three-dimensional case, but it's just visually easier to keep track of what's going on. So if I take that sort of analogy and say, let's just look essentially at a square in a plate that I've pulled out. So I've applied some loadings, I've got a plate somewhere, and I pull a little square out of that thing. Instead of a cube out of the volume, I end up with something like this, where I essentially have my stress components acting, the normal and the shear, the normal and the shears. And then because I'm moving a distance dy, there's some variations in y. So these things are changing. And because I'm moving here dx distance, there's also variations to those stress components in the x direction. And so what is clear is, again, all of these components are nice spatial functions for x and y in this case. So this is now a two-dimensional example. So sigma xx, I can express the function of x and y. And that's why essentially by taking the partial derivative of sigma x with respect to x, because it's a function of x, it has got a contribution that can be a variation of the stress there. Okay, and what we want to look at now is under which conditions is this thing under static equilibrium. And what you see is I haven't pulled in the body forces, so I'm going to ignore the body forces for now. So I want to make the two scenarios without body forces and then with body forces, so that it's crystal clear in your mind what's going on. Okay, so without body forces, so all I'm saying is that there's these tractions there. We switched off gravity, so that's a nice physics switch that we have in FEM that we can't really do in reality. But that's always one of the advantages of modeling, is we can really modify the physics and isolate certain physics and switch other physics off if you want to ask some scientific questions. Okay, but the bottom line is, if I ask myself what is the equilibrium conditions relating what's going on here, I have to start saying, okay, let's look at sum of forces in the x direction and see what we get out to. So if I say let's do the sum of forces in x direction, I get essentially sigma xx plus then essentially that, so minus sigma xx plus essentially that term there. But I have to make sure that if I want to convert the stress down to a force, I just need to multiply by the area. So what I'm going to do is I'm going to pause the video here. I'm going to go switch towards the light board, and then I'm going to develop this on the board rather than just talking you through it. Okay, so let's go towards switching towards the board and do the derivation for this. I'm going to stop this recording.